Hi, my name is Hanpan Chiu. I'm a Senior Technical Manager at SR International. The topic I'm going to talk about today is cross-modal geolocalization. It includes two steps. The first step is code search. The second step is file alignment. In the talk today, we will discuss what is cross-modal geolocalization. Then for the first step, code search, and the second step, file alignment, we will go into the details. We will give an overview about related work. We will also discuss the algorithms for these works. Then we will make the conclusion in the end. This tutorial is about geolocalization, and we focus on image-based geolocalization. It means if we have one query image, we need to know where this image is taken. So the goal is to compute the 3D geodetic position of this query image. For some applications, it even requires to compute the entire 3D pose of this query image. The 3D pose include both position and orientation. So that's the definition of image-based geolocalization. There are many applications about image-based geolocalization. For example, if you have an image that is taken from a long time ago, you don't know where it is, then of course, image-based geolocalization can help you to geotag this image automatically. And it can help you to organize your personal photo library. And the other important application is about a self-driving car or other robotics applications in GPS-denied, challenged environment. So GPS is a typical sensor to provide the geolocalization of the platform. However, GPS accuracy degrades in urban areas. For example, if there are many tall buildings block the GPS signals, the localization accuracy for GPS degrades. However, for those applications require high accuracy, like a self-driving car, it requires even like sub-meter or even millimeter accuracy. The GPS accuracy is just not sufficient. So using the image-based geolocalization technique can help these applications. In addition, camera sensor is typically very cheap, so it's not expensive. It's very popular for any user to use. So that offers a good solution to these applications. The process for image-based geolocalization typically includes two steps. The first step is code search. The idea of code search is to search and match a query image against a database of geo-referenced images or video streams. It is also called database retrieval in research fields. In this process, each image inside the database is associated with a geodetic position or a geopose. There is also a descriptor to represent each image. The code search process will extract the descriptor from the query image and then compare this query descriptor to all descriptors of database images. It becomes a nearest neighbor search problem. The goal is to find a database image that is most similar to the query image based on the similarity between their descriptors. The returned database image will give us the correspondent geopose of the query image. The code search step gives us a 3D geopose for the query image. However, This 3D geo-pose is actually from the database image. It is not the actual geo-pose for the query image. Therefore, the second step, file alignment, will register the query image to the 3D geo-referenced data to further refine the 3D pose of this query image. This registration process typically uses features between the 2D query image and the correspondent 2D 3D geo-referenced data. This step requires detailed 3D information in the database, such as 3D point cloud. It is also called geo-registration in research fields. As what we described in the previous slides, image-based geo-localization requires to construct a geo-referenced database beforehand. This database can be constructed using different ways. The reference data inside the database can be collected using different sensors. Typically, this database will be constructed using the images collected by cameras from the similar ground points. So this problem we called cross-time geolocalization. It is because this reference data may be collected across different time periods, different weathers, or different lighting conditions. So this cross-time geolocalization field, there are already a lot of research works in this direction. However, to collect this reference data in the ground area requires time. So for example, we can see that like a Google self-driving car, they typically will send out the cars to collect data again and again, but it takes a lot of time because you may struck in the traffic. So these days, there are also research works about that to build the database from the aerial viewpoints. So if you send a UAV to collect the aerial reference image, and then now you match the ground query image to the aerial reference data, the collection of the reference data becomes easier. However, the matching between the ground query view to the aerial reference data is more difficult. So we call this problem cross-view geolocalization. The cross-modal geolocalization is even more difficult. However, the reference data can be obtained from many public available resources, for example, OpenStreetMap, or some LIDAR 3D point cloud collected from some organization. So there's a lot of potential in this research direction because the reference data is easy to be obtained from those open source. However, the matching between the ground query image to the reference data collected from different modalities is very difficult. So this is the major difference between cross-time, cross-view, and the cross-modal geolocalization. In this talk, we will focus on this new but challenging research field, cross-modal geolocalization. Now we are going to give an overview about related works in the Coarse search area for the cross-modal geolocalization. For Coarse search to cross-modal localization, there are two most popular reference data sources. The first one is a LIDAR data. The second one is an open source map, such as OpenStreetMap. So we will start the first one, the image to LIDAR localization problem. So the LIDAR sensor typically is more expensive and also is bigger than a camera. However, it can get the accurate 3D information of the scanned environment. So it can build a 3D point cloud of the target environment to create a 3D geo-referenced database for accurate localization applications. So typically, the automotive industry collect the LIDAR data using the ground vehicles. They will install a LIDAR sensor on ground vehicle and to collect the data of the environment and build a 3D reference database and also build an accurate 3D map. So there's also some work that to collect LIDAR data using the UAV or the small drone sensors. So this way is more efficient because you can scan the large-scale environment very efficiently and get a 3D LiDAR data. And then the idea for image to LiDAR cross-modal localization is that if we use the low-cost camera sensor to get some query image, but you use that to match to the accurate 3D LiDAR database for the localization, it becomes a very appealing solution for the accurate localization applications. So we will start to give an overview of this area. As what we described in the previous slide, using ground RGB image as a query data to search and match against a large-scale 3D geo-referenced database, which is built using aerial LiDAR sensor beforehand, is a very appealing solution to this problem. However, this is also challenging because the aerial LiDAR collect data from a different angle to the ground perspective. And also the difference between camera image and the LiDAR point cloud is very big. The appearance changes a lot between the image and the LiDAR point cloud. And the aerial LiDAR also, because of the viewing direction, sometimes you will miss the information along the vertical direction. So for example, when you scan the environment, scan the building, the vertical edge of the building, that the information may miss. So in this area, although this is a very interesting direction for this problem, there are actually very limited prior works for these problem settings. And also for these prior works that they focus on area like an urban area which has the building and use the manually annotation on the building outlines for the match and the query. And the example they show is also very limited. So recently, SRI presented the first deep learning-based approach to this ground RGB aerial LiDAR search problem. So SRI proposed a new multi-model deep CNN approach to learn a joint representation for the ground level RGB image and the aerial LiDAR depth image to solve the cross-modal geo-localization problem. So we will talk about more details about this work. SRI's RGB to LiDAR network is the first deep learning-based method for cross-modal visual code search applications. So the idea is that we started with a standard framework of learning joint embedding model for cross-modal retrieval. So joint embedding is a state-of-the-art technique from social media analysis. For social media analysis, different user and different user groups can have different kinds of data from the web, including text, image, audio, and video. The idea is that the deep embedding space want to group different kinds of data belong to the same user or same user group together in the embedding space. So SRI is the first one to leverage this kind of concept to apply to the cross-model code search applications. The idea is that for the 3D LiDAR point cloud, we project 2.5D LiDAR depth image for different positions and different orientations. And then for each depth image, we pair it with a ground street view image, and then we use this paired data to train an embedding space. The idea is that LIDAR depth and image, which belong to the same geodetic position, should also have a very close relationship distance in the joint embedding space. We use the state-of-the-art triplet pairwise ranking loss function to train these joint embedding models. This ranking loss is widely used in training joint embedding, and is a current state-of-the-art technique in many cross-modal retrieval tasks. So once the joint embedding is trained, all the database LIDAR image representation is already extracted in the joint space. So this joint embedding space is a high-dimensional space. So each data point, like a LIDAR depth image, can be represented as a high-dimensional feature vector. That's a descriptor for the LIDAR depth image. So all the LIDAR depth image can use this descriptor to construct the reference database. And now for any query RGB image, it can also be extract the descriptor by projecting the image into this joint embedding space. Then based on the descriptor, we can find the most closest descriptor from the database to get the LIDAR depth image and the correspondent 3D geotag position. So that is the concept of the code search using RGB to LIDAR network we proposed. One major difficulty to cross-model geolocalization is it lacks a benchmark large-scale dataset. So to address this problem, we created a benchmark dataset, which we call the GRAL Dataset. So to create this dataset, basically we download the street view images from Google using a open source API for different locations. And then we also download the correspondent LIDAR 3D point clouds of the same area, which is collected from the USGS National Map website. So all this data is available online as the given link in the slide. So this is a large-scale data set that can be used to train and evaluate the cross-model geolocalization problem. This dataset includes 550K pairs of RGB images and LIDAR depth maps. It covers 143 square kilometer area in New Jersey, United States. This slide shows some examples from the dataset. The first row shows the RGB images. The second row shows the correspondent LIDAR depth map for that particular position. Because the data collection process is automatic, it may include some misalignment situations. For example, here we show example that the rendered depth map miss pixels due to the aerial collection. Because the LIDAR data collection is from the air, the viewing direction may miss the values along the vertical direction, such as fins under the top of the building. In addition, the scene can change over time. There can be scene difference across time during the data collection. Therefore, this dataset is a challenging dataset. However, it can be a good benchmark dataset to the cross-model geolocalization problem. Cross-model matching is very difficult. It is because the appearance is very different across different data modalities. So one central idea from our work is to use semantic information to improve the results. Compared to appearance information, high-level semantic information such as semantic scene layout is more consistent across different data modalities, so it can further improve the results. So the semantic information we define here is about semantic segmentation that labels each image pixels into one of the pre-trained semantic classes, such as sky, tree, road, and buildings. So here we propose a fusion process for this architecture. So for both ground image and the LIDAR depth maps, we apply two networks, one to extract the appearance information, the other to extract the semantic segmentation information. Then we pair different combinations to project into the embedding space. Then we fuse them together to generate the final results. So this kind of mixture of expert model approach works very well for the database retrieval task. So here for the appearance feature extractor, we use the ResNet 18 model. For the semantic segmentation, we use SegNet to extract the features. Then we leverage the capability of neural networks to learn representation first and fuse them in the final latent spaces, so we can utilize this expert network architecture to focus on subtask. And finally, given a query ground image, the retrieval is performed by searching the nearest neighbor in the latent joint space. However, most of the semantic segmentation networks are used for the RGB images. So one difficulty in our work is that there is no existing networks to perform semantic segmentation on LIDAR depth image. So we propose a new weak cross-modal supervision approach to train a model to do the semantic segmentation for LIDAR depth map. The idea is that by using the pairs of RGB image and the LIDAR depth map, we can use the semantic segmentation results from ground RGB image as the pseudo ground truth to train the network of LIDAR depth map semantic segmentation. So this kind of process will help to train the network for the depth map semantic segmentation. And after the training, we can remove the RGB image and just use the trained semantic segmentation network for LIDAR depth to perform semantic segmentation alone for the depth map. So this slide shows the architecture for our network process. So we can see that we basically propagate the information through the loss function to train this LIDAR depth network. And this approach that works for our system, it improves the results. So we are going to talk about our results in the next slide. We use different evaluation metrics to show our results. For example, R at K, recall at K, means percentage of queries for which the ground truth results are found within the top K retrievals. The median R means the median of the ground truth matches in the ranking. For our evaluation, the test set includes 50K pairs of data collected from 14 square kilometer area. We also implemented different baseline methods. These methods include using the handcraft features or pre-trained CNN models. So from the results, we can see that these baseline methods performed pretty bad on this large-scale dataset. It demonstrates that this actually is a very difficult task, and the dataset is also challenging. However, our proposed RGB to LIDAR model shows promising results. We can see the recall at 1 is 27.6. That means among all the queries, around 27% we can get the correct match at the first return match. The median rank value is 5, is also encouraging by using a deep learning model to this challenging problem. It is difficult to directly compare our approach with prior works in ground RGB to area LIDAR geo-localization area. It is because the query image and LIDAR data from prior works are not available. Moreover, these prior methods use specific pre-processing, which makes them unfit to large-scale applications as targeted in our work. For example, they are limited to an urban setting, and the localization performance depends on the availability of the buildings in the image. Moreover, some works require manually annotating the building outlines of query images. However, if we look at the reported values between the prior works and our results, we can see that our performance is still much better. In addition, we also compare our results to typical cross-view localization model, such as CMRNet. By collecting ground panorama images and aerial satellite images for the test locations in our dataset. So the idea is that for the same area, we use the ground image and the aerial image to represent the same problem setting as a cross-view localization situation. Then we compare the results. Our performance is still much better than the cross-view localization setting at the same area. So this further demonstrates that the potential of the cross-modal geo-localization approach to this problem. This slide shows a more detailed analysis of our proposed approach. So here shows that our joint embedding models, which combines 4 combinations of appearance and semantic cues from RGB and LIDAR images, performed pretty well. This kind of fusion strategy shows a large improvement over the single embedding based baselines. Finally, this also shows that using semantic information improves the results a lot. So that confirms our hypothesis that fusion of the both appearance and semantic information is a good direction to cross-modal geo-localization. Here we show some examples on the semantic segmentation of LIDAR depth images. We use the weakly supervised training approach to train the network to conduct semantic segmentation on LIDAR depth images. Here shows that the results is reasonable compared to the semantic segmentation on the ground image. The semantic information is consistent across RGB image and the LIDAR depth map. So the semantic cue provides valuable information compared to the appearance, and then can improve our results. Here shows some query results using our approach. For each row, it shows the query ground image and the returned LIDAR depth map from the database using the appearance-only information or using our proposed approach to combine both semantic and appearance information. So the red number shows the ground truth rank among the returned match. So we can see that, for example, the bottom right example, using appearance information, the correct match is among the number 18 match. But if we use our proposed approach to combine both appearance and semantic information, the top one match is a correct match. The second row of each example shows the correspondent LIDAR depth map or the ground RGB image for that particular place. So here we can see that although the LIDAR depth information looks very different than the ground image, using our approach, it becomes feasible to conduct cross-modal geolocalization tasks. Now we are going to talk about the works in the second part for code search. For this part, the reference data uses the OpenStreetMap. We are going to talk about the related work in this area. Related work for this problem setting is also limited because cross-modal geolocalization is a new area. So for these prior works, it only focuses on code search because using the OpenStreetMap as reference data, currently all these works doesn't include the detailed 3D information in the database for file alignment. So here we choose two related works in this area because they share the same problem settings. For these two works, the query input for each position is a Google Street View panorama image, and then the authors crop it into 4 different images. It covers the front, back, left, and right viewing directions, and the reference data is OpenStreetMap for their works. The first work we are going to talk about is automated map reading. The idea of this work is to use a 4-bit descriptor to compare the ground image and the OpenStreetMap. This descriptor is called binary semantic descriptor. The idea is that for the 4 directions, front, back, left, and right, it uses 1 bit to encode whether there is a gap or there is a junction along that direction. For example, we can see the right picture about how to encode this information of one geodetic position on the OpenStreetMap. If the front direction has a junction, then the bit is 1. If there's no junction, then it's 0. For the left and the right, if there's a gap between the buildings, then it becomes 1. If there's no gap, it becomes 0. So same for the ground image, because the authors crop the panorama image into 4 different images to cover these 4 directions. So they trained a network to try to classify these images to indicate where there is a building gaps or there is a junction present in this direction inside the image. So they use off-the-shelf pre-trained CNN model and fine-tune it on a training set of 440K images taken from 220K locations across 23 different cities. And then based on the test results on 8,000 images, it achieves 75% accuracy on the classification of whether there's a built-in gap or there's a junction in the image. So it proved that this descriptor is reliable to detect the gaps and the junction. However, this descriptor is not powerful enough because using this 4-bit descriptor, there are total 16 different situations. The most common one is 0000. That means no gaps and no junction for a particular position. And that actually takes, I think, at least 50% of time for this situation. So this descriptor is not discriminative for geolocalization using just one descriptor alone. So to improve the power of the descriptor, the authors propose an idea to connect these descriptors along the route. So the idea is that every 10 meters they will sample a position and then to connect this short 4-bit descriptor together. Then during the search, they can compare this connected route descriptor from the query route to the database. Then they also encoded the turn pattern to indicate whether there's a left turn or right turn present between the connected positions. The authors also created a large-scale dataset for experiments. The dataset includes both the ground street view and the OpenStreetMap data for 2.5 square kilometers region. It includes more than 6,000 locations in this dataset. It has 150 test routes, and each route can have at most 40 locations. That means 400 meters, because they sample the position every 10 meters. So here shows the results. If the authors only use the single binary semantic descriptor, the accuracy is pretty low. However, using the concept of route descriptor and the turn pattern, they can achieve pretty good accuracy if the accumulated route length becomes 400 meters. So that proves the concept works, because the idea to improve the power of a descriptor by connecting the BSD works. The same research group also proposed a follow-up work. The idea is to use a more powerful deep learned feature vector to replace the BSD in the same problem settings. So here, this slide shows the network architecture for their idea to represent the data. So they extract the features from both images and the maps and to project into a low-dimensional embedding space. So this embedding space is trained using the typical data augmentation technique and the triplet loss function. So the trained embedding space can encode the query image and the reference OpenStreetMap data into a low-dimensional vector. So it's 512 dimension vector. Then the authors use the same route descriptor concept to connect the embedded space vector to improve the power for geo-localization. So by connecting the different descriptor along the route, it can improve the performance by searching the database. It's the same as their previous work. They also created a new test dataset and a training dataset. The results shows that their performance works better than their previous work because the embedded vector they learned is more powerful than the binary semantic vector. So this slide shows some examples about their test results. From the left side is a query image. It covers 4 viewing directions: front, left, right, and back. The right side shows the return match from the OpenStreetMap database. So we can see that the appearance information between ground image and OpenStreetMap is very different. However, for this kind of problem setting, using the concept of route descriptor and the deep learned vector can get some reasonable results. Now we are going to talk about the second step for cross-modal geolocalization. The second step is file alignment. We are going to talk about the related works in this area. There are 2 approaches for file alignment. The first approach is direct 2D 3D registration. The idea is to match features between the 2D query image and the correspondent 3D point cloud for post-refinement. The second approach is registration using 2.5D rendering. The idea is to render a 2.5D view from 3D point cloud using an initial pose computed from Coarse search. Then the entire problem becomes the matching between the 2D ground image and the 2.5D render view. Through the feature matching, it can get the correspondent 3D values to refine the pose for the 2D query image. We will start by talking about the direct 2D 3D registration. There are many works related to direct 2D 3D registration methods. However, these methods typically assume the 3D point cloud is constructed using structure from motion techniques. That means it's from the multiple camera images. So through that construction process, the 3D information and the 3D representation has a correspondent 2D appearance information from the images. So for cross-modal geolocalization, the 3D point cloud typically is from the LIDAR sensor, so it does not have the 2D appearance images. So there is some work to train a random forest classifier to directly match the 2D and 3D descriptors to get the refined pose. However, this area is still limited for the cross-modal direct 2D 3D registration problem. Currently, most works to cross-model file alignment focus on registration using 2.5D rendering. We are going to talk about some representative works in this area. The idea of this approach is to render 2.5D view from 3D point cloud using the initial pose. The initial pose is from the Coarse search step. So once the rendering is completed, it can leverage the available registration technique, such as those techniques from the cross-time geo-localization for the 3D pose refinement. So for all the details of this technique, we can refer to the cross-time file alignment section in this tutorial. However, if there is no appearance information in 3D point clouds, for example, there is no color information, then the problem becomes image depth registration. It is very difficult. For this kind of problem, there are works using the traditional semantic features, such as matching the skylines, building outlines between the image and the depth map for registration and file alignment. We are going to talk about these works. We are going to show the semantic geo-registration works we did before in this area. So for each ground image, we first compute the semantic segmentation of this input image. And then for the 3D reference data we have, we use the post prior, which is from the code search results, to render the 2.5D depth maps. And then for the geo-registration, we extract the edge from the render depth map and the semantic segmentation image. Then we compute a distance map from the edge image. So the distance map means each pixel represents the distance to the closest edge pixel. Then we apply a very famous technique called modified chamfer matching, which will use a template to search over a bigger distance map by summarizing all the transform values for the edge pixels. Then the best match results indicate the geo-registration position. So here we apply this technique by registration using the skyline. So for this skyline matching, we define the refinement is only successful if there are sufficient portions of skylines are observed. So here we define 75% as a threshold. Using skyline matching through the semantic geo-registration can refine the heading of the pose, because the skyline actually indicates the heading direction using the 3D geodetic information from the database. So here we show that using an initial pose, then the blue line, the horizontal line, shows the skyline in these animation examples. And then the white vertical line shows the ground truth heading direction. The blue vertical line shows the refined heading direction using the skyline matching from the semantic geo-registration. So we can see for these examples, if we use the 90% visible skyline as a threshold, the red portion indicates where there is a successful sky matching cases. The green one shows that if we use 75% as a threshold, and that's actually the actual threshold we use in our experiments, then green portion shows indicated the successful match situation. Then the average heading error registered by the sky matching is around 1.29 degree, and more than 50% of successful rate during this scenario. However, sky matching has its limitation. In urban city, sometimes there are occlusions to occlude the skyline observation. So here shows some failure cases, like for number 2 and number 4. Basically in the image, we cannot see a large portion of the skyline. So it's hard to use the sky matching to compute the heading for the post-refinement. One application about skyline matching and semantic geo-registration is to use for navigation to help the applications such as self-driving car. So for all this semantic geo-registration heading correction information that can be fused into a navigation engine and then fused with other sensors such as GPS and the visual features, it can use to further improve the estimated pose to improve the accuracy compared to GPS only results. So that can help the self-driving car applications. Traditional techniques for image depth registration has its limitations. For example, the one we just talked about, the sky matching, doesn't work well for situations in the urban cities. Recently, there are works to apply the end-to-end deep learning pipeline for this problem. So the first work we are going to talk about is CMRNet. This work using I think it's the first end-to-end deep learning pipeline for image depth registration to 3D pose refinement. So the idea is that they first project the LIDAR point cloud to a depth map using the initial pose that can be from the code search results. And then if we project all the depth information into the image map, there are some situations that it will have the duplicate information for the same 2D position. So they also apply an occlusion filter to filter out the information behind the foreground object through the projection. So it makes the depth map looks more realistic after projection. Then they use the network architecture from the PWC-Net for their application. So PWC-Net is a famous network architecture for optical flow estimation. So basically it trains a different network layer to replace the traditional optical flow estimation pipeline. So the authors for CMRNet modify this network architecture for their purpose. So there are a few major changes. The first one is that they use two branches of the encoder for RGB and depth image. The original PWC-Net is to use two branches for two different images. But now because CMRNet need to handle image and depth, and they are very different information. So they also decouple the feature parameter extractors by removing the weight sharing. They also remove the upsampling layers and attach the fully connected layers after the first coarse balloon layer. Then they have two branches in the end for rotation and the translation after the flow estimation. The loss function they use include two parts to take care of the translation and the rotation for the post-refinement. Here shows some results from CMRNet. By starting from an initial pose within 3.5 meter and 17-degree error range, they can achieve pretty good results. It's around 0.27 meter and 1.07 degree accuracy. So these are the entire pose accuracy, cover both 3D location and 3D orientation. So here also shows some visualization of their examples. So we can see that they predict pose, the file alignment pose to project the LiDAR point cloud to the 2D image compared to ground truth is pretty close. The same authors from CMRNet also propose a follow-up work. This follow-up work still uses PWC-Net as a backbone network for flow prediction. However, instead of training to predict the 6 degree of freedom 3D pose directly, they train the network to predict the pixel displacement between the RGB image and the projected depth map. Then they apply RenSec on the point matrix predict from the CMRNet++. In this approach, they show they can improve the results compared to their previous work. Now we have talked about that the related works in the cross-modal geo-localization. We are going to talk about the conclusion. Image-based cross-modal geo-localization is a difficult research problem. It is because there is a large difference in appearance from one model to the other model. However, it has huge potential and can make big impact to many applications. So far, there are limited works in using deep learning for this problem. So this opens many research opportunities in this area. So here we show an example about the potential application for cross-modal geo-localization. The left side shows the input ground image. The middle part shows the 3D depth map from the reference database, which has a LiDAR point clouds using the cross-modal geo-localization results. Because we can get the depth map from the database based on the geo-localization results, it can support the augmented reality insertion based on the depth map. So here we show that it inserts some vehicles on the road and can handle the occlusion nicely because it gets the 3D information from the reference database. So I hope this gives us a good motivation to all the audience for cross-modal geo-localization. Right, thank you.